In chapter 14, we gave symbols. Hey, Terry. And we call them like, right? Remember, sigma molecular orbitals, pi molecular orbitals, those sorts of things. Well, now we're going to have little a1, little e1 are going to be our molecular orbitals and on. And these are coming from the character tables. Right? If you have an irreducible representation that's big A1, that's the irreducible representation, or irrep. But its molecular orbital would be little a1. Okay? So what they're doing is these little building blocks that I was referring to, these irreducible representations, we're going to use them as our energies, as our states, as our molecular orbitals. And we can even identify possible transitions or rule out possible transitions, okay? Spectroscopic transitions. So a lot of this, I think, from character to irrep, I'm just going to leave that to the reading, because we're going to hit a lot of it again right here if we take a hard look at one of these characters, one of these point groups. And I want to look at tetrahedral. But and again, they're kind of jumping ahead a little bit. But for example, can you say an integral is 0? We're going to be able to look at these character tables and be able to predict whether integrals are 0 or not. Now why? Because usually you have 3 things in there, right? This is what one might look like that we're going to work on for a particular point group. It could be octahedral, tetrahedral, D3H, it really doesn't matter. We're going to figure out these integrals. But the point is when you have d tau, x, y, z, you have 3 dimensions. When we had just an integral of 2, you have area, right? And a part of area that's overlapped if it's equal to a number. But if you have 3, you actually have a volume. And what they're trying to say is that, man, if this guy is not equal to 0, if there actually is some overlap there, then no matter how you look at that overlap, that 3-dimensional object, right, that the overlap is, no matter how you look at it, you get the same volume. Does that make sense? You have, just imagine 3 surfaces, right? And at some point they overlap. Is this overlap non-zero? If it's non-zero, the integral is not 0. And what would the overlap look like? It's got to be some 3-dimensional chunk of something, right? Just 3-dimensional shape. Who knows what the shape is? But the point is, no matter how you look at that shape, you get the same volume. Does that make sense? Because it doesn't matter how you look at it, you have to have the same volume. So what they say then is that for that to be equal to non-zero, that integral has to span the totally symmetric irrep, A1. And we'll see what that means mathematically by the end of the hour. Okay. And that's about as close as I can get to giving you some idea there. So let's take a look at this tetrahedral point group. Where is it? Tetrahedral. So find in your notes the tetrahedral TD. There it is. It's I have it on page 3. I'm not sure what your page is. But the tetrahedral point group, TD. TD. Okay. So let's just point out some things for this point group, TD. So did you locate it?
Yes.
No, it says a cubic group.
Yeah, it's under the cubic groups. The first one under the cubic groups. Did you locate it? Okay, the first thing I want to mention here is that H, that's the number of operations, the number of symmetry operations. Because they didn't want to list them all out. For example, you have 8 C3s. So technically, they should be listing C3, C3 prime, C3 double prime, C3 triple prime, go all the way out to C3 with 8 primes on it. They should have 3 C2s listed there. They should have 6 sigma Ds, 6 S4s. Okay. Does that make sense? So there's actually 24 symmetry operations. They just kind of abbreviated it. One other thing we should notice is sigma D. Sigma D is on, let's see, I found that here. We've talked about sigma V, a reflection that contains the principal axis. We talked about sigma H, a horizontal reflection that's perpendicular to the principal axis. And now there's a sigma D. There it is. It's on page 429. And what it looks like is all it does is it bisects a C2. So we really don't even need to worry about it. Because remember in our table where we're identifying point groups, sigma D doesn't even show up. So I'm just kind of showing you what it is, what it looks like. It bisects two C2s. And it shows up in these tables. But we never need to find it, thank goodness. Okay, it's not very easy to find. It is a special reflection. Okay. So those are all of our symmetry operations that are listed up there. There's 24 of them total. Okay. What else do I want to mention? Okay. I don't want to skip anything. The entries in these tables, those are called the characters. They're abbreviated like a little chi there. Characters. Okay. And I can give you some information about them. That, for example, if you look at, if you sum the diagonal on the, we're not seeing the matrices, so it's kind of hard for you to see this. But if you sum the diagonal, that's what the 3 or the 1 means. It also means, for example, if you have a 3, here, you'll always have an E. Okay, that for the A1, where is it? Well, let's just put it this way. I don't think it really matters. But if I offer some ideas, it sometimes helps you remember stuff. Like if you have a molecular orbital that's triply degenerate, okay, that's when you're going to see these E irreps. If it was, what was it? I forget. Oh, that was double. Triple is T. Triple would be big T. Double is E. So these points aren't very important, so I'm not going to spend much time on it because I don't think you're ever going to see it. But that's where some of these letters are coming from. You see them? T's and E's. Doubly degenerate. You see E's for irreps. So these are our irreps, irreducible representations. The top one is our totally symmetric one. Did you notice it? Look, it's all ones. It's all ones. And if you're going to add all the characters for that totally symmetric representation, so we're talking about A1, and every one of them has it. Sometimes there's it's always the top one, and it's all ones. If you're going to sum up all the characters for that totally symmetric representation, a common mistake is just to add these up, 1, 2, 3, 4, 5, and call that 5 as the total. But it's not. There's actually how many operations? 24. So if you add up all those ones, actually you can get 24. So just remember that, because we're going to need that idea coming up later. Yeah, A1 is the totally symmetric, irreducible representation. You'd call its molecular orbital little a1. Right? If the character of the principal rotation is a positive one, and then they call it, you get an A irrep. If the character of the principal rotation is a negative one, you get a B irrep. right? So they're not degenerate. If they were degenerate, then you'd have the E's or the T's. But that's where a lot of these little symbols are trying to come from. Okay, and then on over here, these are how these functions transform. So what that means is if you would take these functions and how do they overlay with this A1 irreducible representation? If you took that function x squared plus y squared plus z squared and overlaid it with this A1 irreducible representation, however you want to imagine it, you get some substance. You get some volume that won't go away. So the integrals won't vanish. Likewise, so that's why, and there's not very many integrals that are like that. There's not very many functions that they list like this. But why do they list these out? I don't know if you recognize them. Like, do you see how they have function x, y, z? They have an xy, an xz, a yz. I don't know if you recognize these little functions. Let's see if I can find what page that was on, help you remember. Page 359. Here it is. Do you remember seeing these, page 359, what orbitals are those? Those aren't p orbitals, those are d. These are d orbitals. These are d orbitals, right? And look at the little subscripts on them. There's a z squared, an xy, a zx, x squared minus y squared, and a yz. Exactly the same stuff they have up here. So what they're really not talking about those functions per se. They're talking about d orbitals. That's what they're trying to get at. If you took a close look at p orbitals, page 358, right? What's the little subscripts on the p orbitals?
Z, Y, X.
Z, Y, and X. So they're not talking about the function x, y, and z. They're talking about p orbitals. That's what they want you to realize. Okay? And so that's what I want you to realize, that these x, y, and z, these are p orbitals, right? So that's on page 359 and 358.
So they're not, so
Okay.
even though in the past they've been using the coordinates, or the
They are referring to these orbitals, page 359, 358, d orbitals. You know that you can have you have a mathematical function to represent it. Luckily, they're not giving us all that information. All they're saying is just, look, this is how we labeled this d orbital, right? It was the xy d orbital. And if you want to know exactly which one it is, you can look it up in the book. If you want to get its function, great. You know, it's going to be an ugly thing. All they're saying is that orbital, dxy, transforms, it has symmetry of this irreducible representation T2. That's what symmetry follows, that irreducible representation. Likewise, for the tetrahedral point group, all p orbitals, where there's 2p, 3p, right? They're following the T2 irreducible representation. And what does this mean? What's the application? Wait a little bit, and you'll see why we're hitting on all this stuff. Okay. That's what all I wanted to talk about. I think so. I'm going to get to the problems here. Okay, so I kind of jumped ahead a little bit, but that's okay. Where did we go? Here we are. Okay. So this is what the homework is going to hit on a lot. How do you pick these vanishing integrals? How do you pick selection rules? So page 443 on the top. And I want to write a little expression here first. Okay, so the big test to determine whether an integral is going to vanish or not, we'll also be able to determine selection rules, is through this. I kind of scribbled out this expression, right? Now the sum of all the characters has to equal a constant times the sum of all the characters for A1. If we can get, and you'll see, once we apply it, you'll see what I'm talking about, I think. I'm just kind of give you a broad overview right now. If this holds true, then we can say, oh, this transition will occur, or this integral will not vanish. There's an actual three-dimensional object in space. No matter how you look at it, it spans A1. It's completely symmetric. Okay, it won't go away, just by symmetry. So let's take a look at a few of these examples to give you. Oh, I guess we should take a look at page 443 top. Page 443 top is the general rules. Okay. So let's say you have page 443 top says, just if you don't have your book, let me run it through with you. You have an integral f1, f2. Does it equal 0 or not? So page 443 top, there's 3 steps. And they say, first, decide the symmetry species of the individual functions f1 and f2 by reference to the character table. So you look at the character table and see whose irreducible representation each one of these functions follow, right? So what am I talking about? Remember the irreducible representations. It could be an E, right? Any of these guys. If you're, right? Depending on what point group, they have to tell you the point group you're interested in. And then one of those functions will follow, I don't know, perhaps this one. The other function, maybe it follows this one, irreducible representation. Somehow they have to tell you that in the question. Okay. And then it says write their characters in 2 rows. Well, let's say we just wrote this guy's characters. Here they are. I wrote this guy's characters in 2 rows. Okay. Multiply the numbers in each column, writing the results in the same order. So you just multiply them. Remember, there's 1, there's 2 of these guys. Don't forget about how many there are. Right? So we multiply through, add it all up, and see if this holds true. Okay, so this has been very broad and very ambiguous. We need to see an example. Let's take a look at page 443 on the bottom. Now, if you don't have a book, page 443, example 15.4. So, Ricky, just turn around with Brad there. I'm looking at page 443, example 15.4. Okay, so what it says is, may the integral of the function f equals xy be non-zero when you evaluate it over a region of the shape of an equilateral triangle, centered on the origin. So what you have to do is first figure out, well, let's just look at the method. First, note that an integral over a single function f is included in the previous discussion. Okay, where are they? Okay, let's just jump down to the answer. An equilateral triangle has a point group D3H. So you got to figure out what point group it is. Remember, we follow that big long chart to figure out which point group the equilateral triangle is. And it falls into D3H. Great, we got it. So if we refer to the character table of the group, okay, so let's take a look here. So D3H, let's find D3H and work this out and see where they're coming from. D3H. Here's D3H.
We have 6 operations.
Okay. So what we're going to do is find out what x is. Here's x. So that's going to be, I can write it up here. What I'm doing is I'm copying x's characters, right? 2, -1, -1. Right? Writing down all those characters. And then times f2, right? Because I'm pretty much following the steps on the top of page 443. So f1 was supposed to, they said x times y. So f1 must be x, f2 must be y. And I think they both follow the same irrep. Right, so I got to copy all those characters again. 2, 2, -1, -1, 0, 0. Right?
So in columns will be the straight line.
Yeah, so what I'm just copying, right? All I did is I copied them.
So this is multiplied the
Right.
in each column.
Now we have to multiply the numbers in each column. So remember, yeah, columns going this way,
Okay.
right?
Click those Z's again?
Because, oh yeah, right here. Because they said F1 is X, F2 is Y. And they're, so I took them both from the same row because they're both follow the same irrep. So I just wrote them both up there. Okay. And then they said pretty much multiply. Let's see if we Okay, so then we sit there and we multiply them together, right? We get 4, 4, 1, 1, 0, 0, right? You add this stuff up, 8, 10. Okay.
So then I just
Spans representation. So you can, there's a couple ways you can do this now. You can say 8, 10, right? It's not going to add up to be D3H. See how this sum was 12? Because our little expression was it's 0 if, here it is, sum of all the characters, sorry, it's not 0, right? Well, the sum of all the characters is some constant times the sum of all the characters for A1. The sum of all the characters for A1, keep going the wrong way here. Which way is it? All right, here's A1. The sum of all its characters is going to be how many? Yeah. Well, there's going to be 12 total. Right? Because we have to remember there's 3 here, 3 here, 2 here, 2 here. So, but everything's 1, so you pretty much just look up here and see the sum of the characters. The sum of the characters for A1. Pretty much you just always look there. Because everything is, it's always 1s. So if we take a look at the one right below it, self-test 15.4. Right? In self-test 15.4 on page 443, can the function x squared plus y squared have a non-zero integral when integrated over a regular pentagon centered on the origin? So the first thing you got to do is find out a regular pentagon, go through that table, and see which point group it comes into, right? So we've had practice on that. I'll give you the answer. You can, that's a you do. You can prove it to yourself. But it'll be D5H. That's what it said. Self-test 15.4, page 443. Right, so now we're just doing page 443, the very bottom, self-test 15.4. Can the function x squared plus y squared have a non-zero integral when integrated over a regular pentagon centered on the origin? So, first step, which point group are we talking about? D5H. So then you find D5H. Here's D5H. All right. D5H. So we found D5H. And then what's x squared plus y squared? Where's x squared plus y squared? Oh, there it is. Yeah. So it definitely, it matches the totally symmetric representation perfectly. So yes, right? That the integral will definitely be non-zero because it matches perfectly A1. Okay. mathematically you could say that it would be a constant of 1 times the sum of all the characters of A1. So it works. Okay. Make sense? How about another one here? Let's see. Page 447. There's another one that's a good one. Okay. Page 447 is kind of nice. Yeah.
I'm sorry, how come the sum of it would not become 6?
Because, remember, they want to abbreviate these tables. So there's actually 3 rows, like for in this one, there's actually 3 columns for sigma v. 1 sigma v prime, sigma v double prime. Because there's 3 of them. So the actual number of symmetry operations is actually 24. So if you're going to add all this stuff up, there's actually 24 bloody columns. They just abbreviated it. Right? Because how many symmetry operations are there? There's 24. So if you add up 3 plus 3 plus 1 plus 2 plus 2 plus 1 plus 3 plus 3 plus 1 plus 2 plus 2 plus 1, you're going to get 24. There's 24 symmetry operations. And each one has a 1. So the sum of all the characters for A1 is, I would say, always H. Okay. If we take a look at page 447, so that was just playing around with will functions be 0 or not. Well, now what they're asking about, page 447, is this part, selection rules. Okay. Now the dipole moment, so it would look like it's pretty much how they, well, no, let's write a mu in there. Will this transition occur? Right? Will the transition go from here from 1 to 2 with an electric dipole moment? So the dipole moment transforms as x, y, or z. So you have to do this problem 3 times. When they're talking about selection rules, will this transition occur? You have to multiply. I see there's going to be 3 functions here. Function 1, function 2, and the x. Then you have to do it again with the y. Then you have to do it again with the z. And remember where you find them. Just find them in the character table. The x, the y, and the z. Right, here's how x, for example, if it was d something h, x and y would transform with this irrep, and z would be with this irrep. So when they're talking about page 447, it's going to be a little more work. So if you take a look at page 447, right there in the very middle, okay, they say, right in the very middle, they have this table, and they say, okay, they're talking about C2V. Let's see. And they want to know what transition. I think from A1 orbital in water. Okay, they want to say the little A1 orbital to the little B1 orbital. Okay. Can this occur? So I'm on page 447, the problem they worked out in the book. Can A1 orbital, can that transition occur via dipole moment transition? Okay, electron dipole moment. So what they did is they listed in this column, it doesn't really matter which one you list, top or bottom, you're just multiplying numbers together, right? So you have B1, they listed it here. They listed their A1 right there. Then the center, they have to do this 3 times, right? Once with all the x characters that transform as x characters, irrep that transforms as the y, irrep that transforms as the z. And some of them might be the same, like x and y might be the same. And then you do your test. You multiply them all three together, f1, f2, f3, add them all up. And sometimes what they do is, instead of adding them all up, they just say, oh, look at this. This guy matches, I don't know, the E1 irrep or something. So then you don't have to worry about it. You know what? If your answer matches something in here, like I say, it matches this guy, you just quit right there and say, no way. He spans, the technical jargon is, he spans V2U. So that integral, that transition cannot occur. The integral is 0. Because if he completely matches one of these, there's no way he's going to match that one. There's no point in even adding things up. But you can. It won't hurt anything. Okay. Example 15.7. Let's try this one. Let's just work this one out completely. On example 15.7, I'm on page 447. Is px to py an allowed transition in a tetrahedral environment? We were playing around with the tetrahedral point group earlier. Where did it go? Okay, here it is. Let's clean it up. Okay, so they want to know, is it, I don't think I can draw on there. Shoot, I'll have to do it on the chalkboard. I lost it again. There it is, tetrahedral. So here's our point group. And they say, is px to py an allowed transition in a tetrahedral environment? So we have our character table right here. Okay. So x transforms as T2. Y transforms as T2. Right? And now in the center we have to try x. All right, they have to try y. They have to try z. And I do this 3 times. So let's put down all the T2 characters. Right? So put down all these characters, top and bottom. I guess we should list them out. It might make it easier, right? Let's list it out. E8C3, 3C2. I didn't give myself enough space. 6 sigma D. 6 sigma D, 6S4. Okay. And now I've got X, Y, and Z, so that's T2. Well, these are all the same, aren't they? So 3, 3. Yeah, right, they're all X, Y, and Z are all the same. Pretty much doing that one, right? 3, 0, negative 1, 1, negative 1. Did I write that down? 3, 0, negative 1, 1, negative 1. 3, 0, negative 1, 1, negative 1. 0, negative 1, 1, negative 1. And X, Y, and Z are all the same here. Right? So I guess we don't have to do it 3 times, because aren't they all the same? So now we multiply all this stuff together. See what we get. Okay. Now this is where I screw up a lot of. It's easy to screw up. Remember, you've got 8 of these stinking things. So when you multiply down, it's really 1 times 3 times 3, right? We're multiplying them all up. And then we'll add up everything, and we'll do our test. Do the sum of all these characters equal a constant times the sum of all the characters of A1. Right? So 3 times 3 is 9 times 3 is 27. Right?
Yeah.
No, I mean, like, how
I'm
can we
just
get
copying
3
it.
sets instead of just 2 sets?
I have to do
Oh, 1.
the transition. So here's my px, here's my py. In the center is my dipole moment. And this transforms as what, or what? Dipole moment transforms as x, y, or z. So that's why you pretty much have to do this 3 times. But my x, y, and z I'll transform as this guy. So that's why I put this here. And where are you starting at in this transition? I just put that guy up on top. And then where am I ending up? I just put him on the bottom. Okay. Make sense so far? Yeah, everything's T2, so I'm pretty much cubing T2. Right? So, but it's a little more complicated than that, because don't forget, remember you have 8 of these guys, and you're multiplying through. So you have 1 times, so you're 27, 8 times 0 times 0, 8 times 0, right? You still get a 0. Let's see, a -3, -3, positive, yeah, it still gives you a -3. Okay. This one you get 6. Here you get -6. Okay. So now you got to add everything up. Remember, that's the big test. Add up all the characters. Okay. So if we add up all the characters, let's write it up here. The sum of all the characters, does that equal a constant times the sum of all the characters of A1? Is that how you? I'm kind of making up my own little function here. The book doesn't really have it. You see what I'm trying to say? I'm trying to say, add up all the characters. Do you get a constant times the sum of all the characters of A1? Okay, so you add up all these characters, what do you get? 20. Let's see, this guy's gone. You just get 24, right? You agree? Don't just get 24? Brad, you agree with that? Okay. A constant times, okay, what are all my characters for A1? If I add up all those, what would I get for tetrahedral? What do I get if I add up all the characters for A1? Add them all up, what would I get? Remember, there's an easy way to do it. Just look at what?
24 times 24.
How do you get? It's 24. So really what you got to do is take 1 times 1, 8 times 1, 3 times 1, 6 times 1, 6 times 1. Or just look where? Yeah, because there's 24 of them, and everyone's a 1. So the question is that a constant times 24? Oh, yeah, it worked, because C would just be, C will just be 1. So will this transition occur? Yeah, you could. So this is all. It'll occur in the X. We could put in Y. We're get the same result. We put in Z. We get the same result. So sometimes the answer might be, well, if these would have been all spanning different irreducible representations, right? Maybe an X is here, a Y here, Z is up there. Then you can say, oh, it's a Z polarized transition. if only the Z one worked. Or it's an X polarized transition or a Y polarized transition. Here you just, it's allowed. It's an allowed transition. Polarization doesn't matter. Okay?
So then when it says the sum of the operations, that's not the sum of the x and the y and the z.
Be careful with your notation. Be careful with your speak. The sum of the operations. What do you mean?
I thought it meant the x
What-
plane, y plane,
are you talking
z
about-
plane. I guess because I noticed you have 24 there, which makes sense with that. But is that just for the x plane, not to
X
the y
plane.
plane or the z plane?
No, don't use the word plane. We're talking about a transition. Can this transition occur? If you have what was a dipole moment?
There's the differences in electronegativity.
Yeah, you have some molecule. You have some molecule. That's some weird, funky shape, and then oh yeah, it has a dipole moment. So that means it's polar, right? And has some direction, right? So sometimes they pointed them like this. All right, dipole moment. Okay, so we're not talking about the molecule's dipole moment. We're talking about this. Well, I guess in a sense we are. It's interacting. That if you have plane polarized radiation, remember drawing light, but we're really interested just in the electric field, right? So how is it polarized? It could be polarized in the x direction. It could be polarized in the y direction. Those are your only three choices. So will one of these allow that transition to occur between you name the state and you name this other state? Just name them, right? And remember, what are your states to pick from? The states you can pick from are little a1, in this case for tetrahedral, little a1, little a2, little e, little t1, little t2. So you can pick whatever states you want and say, hey, will this transition occur? Ah, okay, a1 to little e1. Will that transition occur? So what you have to do is exactly the game plan over here. Write out little a1's, all of his characters. Write out E1, all of his characters, and then X, Y, and Z in the middle. But what's key, I think, and I often forget to do this bloody part, write this top part. Because if you don't have the number, you're going to be way off. There's 8 C3s, not one of them. So this is 8 times all this stuff, 3 times all this stuff, 6 times all this stuff. Okay? It's a common mistake. So once you get the mode down, I almost think of it as normalization. You have some initial starting point in my head. And for normalization, it was something like this, right? I'm not sure how you thought about it, but that's how I thought about it, right? For what we're talking about now, vanishing integrals or transition rules, this, write your equation that makes sense to you. This is my starting point. That I have to add up all the characters. And is that going to be a constant times the sum of all the characters of A1? So this is my starting point. So how the heck do I get this stuff? I got to make a table. So this is the initial thought that goes through my mind to remind me to do this. And then I find the sum. The sum would be on the bottom. And it doesn't have to be all 3. They might just say, hey, is this function, and like they said, is this function non-zero over this orbital? So you just have, for transitions, you have 3. Other things, you might just multiply 2 functions together. Just have 2 rows then. See, we can get, we're about out of time. But so give it a shot.
So then this class is on Wednesday?
That's what it looks like.
Oh, sweet.
We can have a review day.
That'll be good, because I got my Spanish test.
But if the review day,
That was killing me.
because I think we're going to have one more maybe even 2 more chapters after this. If the review days, I'll give you a heads up, review days a waste of time. We're not going to do it again.
Okay.
Because our last review day we had, waste of time. It really was. I mean, some people showed up, but even the problem, your mind wasn't there because you're so busy, and it was just allowing you to procrastinate, it felt to me. So make sure that you ask a lot of questions